This video is about analog oscilloscopes. It corresponds to section 15.1 of Applied Analog Electronics. Now, because we don't use analog oscilloscopes in this class, it's really not essential material to watch the video. It's more just to give some history and kind of a cool looking device. All right, so let's take a look at an oscilloscope. This is a moderately old analog oscilloscope. I bought it used on eBay some time ago. It looks like a nice flat panel here, but what you don't see is that there's about 1.5 feet of box behind here, and the thing weighs about 25 pounds. The way an analog oscilloscope works is that there's a phosphor screen here which has a vacuum, it was on a vacuum tube. And that vacuum tube actually runs the entire length of this box. And what the vacuum tube is doing is it's shooting an electron beam at the phosphorescent screen, and where the beam hits the screen, it causes light to be emitted. And it's sweeping the beam across the screen from left to right, according to some time base. Basically just using a ramp waveform and some plates to set up an electric field to deflect the beam. It's got another set of plates to deflect the beam vertically. And the way this thing is currently set up is it's sweeping across there once for channel A, which is on this one, and once for channel B, which is over on this one. And we can slow down the sweep to get a clearer view of what's going on. There it's sweeping channel A, now channel B, now channel A, now channel B again. And it's just alternating between channel A and channel B. And there's actually a setting for that, because instead of sweeping all the way across for channel A and then all the way across for channel B, we can alternate quickly between them. It's called chopping them. There's a button here to do chop mode rather than alternating mode. And now it's doing channel A, channel B, channel A, channel B very quickly, fast enough that you can't see it. When you're looking at very slow signals, then this chopping back and forth is a really nice thing to be able to see both signals and not have a big pause. If you're looking at very fast signals that are as fast as the chopping, then it doesn't help. The chopping interferes with you seeing the proper signal, and it is better to say, let's look at all of channel A and then all of channel B. Okay, let's speed this up again. And you can see that this knob that I'm controlling here is basically the control for how fast are we sweeping across there. And as we get faster and faster, eventually we get something that looks like just a steady waveform. So that every time we're sweeping across there, we're going high, low on channel A, and then we're doing the same thing on channel B. And the way we keep these things synchronized is this other set of controls over here, which is the trigger controls. And we can trigger on a rising edge or on a falling edge. And you can see that that changes when the trace starts. We can also decide whether to use AC coupling. We can do some high frequency rejection. And we can set it to DC coupling also. And for what we're doing, it doesn't make much difference. We can have internal, which is basically using some of the information from channel A or channel B. We can use line, which is a 60 hertz triggering, and now you can see that's not synchronized with our input signal. We can have an external triggering, which is off of this banana plug here. But internal triggering is what we're going to be using most. The reason I'm telling you about all these things is, one, just to give you a little bit of history, but also because we have very similar controls on the digital oscilloscopes we're going to be using. And so having some idea where some of the naming and stuff comes from, like what the sweep is, it's sweeping across the beam across here. The digital scope doesn't work in exactly the same way, but the terminology for triggering and sweeping and stuff like that come from these old analog scopes. Okay, on the bottom here, we have controls for the vertical deflection. So the top part up here was controlling the horizontal deflection of the beam. The bottom part controls the vertical deflection. And we can either do channel 1 or channel 2, or here I've got both buttons pressed, so I'm doing both. If I release one of them, now I'm only doing channel 1, or I can do just channel 2. I've got a little thing that says, well, what if I'm doing internal triggering, what is it? In vert mode, it says, well, if you're sweeping channel 1, then it's channel 1. If you're sweeping channel 2, it's channel 2. I can say, hey, I always want to use channel 1 no matter what. Or I always want to use channel 2 no matter what. This control, volts per division, basically controls the gain of the amplifier used for doing the vertical deflection. And I have got some problems with internal problems with the switch here that sometimes I have to twiddle it a little in order for it to make proper contact. Again, it's a very old scope and not in that great a shape. There's a control here for AC or DC coupling for the input. Right now it's DC coupling. I can switch it to just say, where's ground? And now you can see it's not triggering very well on channel 1 because channel 1 doesn't have a trigger. If I always trigger on channel 2, it triggers more uniformly because channel 1 is always ground now. And that tells me where the 0 voltage is for channel 1. If I go to DC, I can see that this is going from 0 to a little less than 2 volts. Actually, it's probably going all the way to 2 volts. This oscilloscope is not properly calibrated. Again, I got it surplus and didn't get it fixed. Okay, this is a similar set of controls over here for channel B. I can do all the same stuff. There's a position here. If I say, hey, I don't really want the 0 there, I want the 0 to be here, I can move this thing up and down. And you notice there's a horizontal position control also if I need to adjust things with that. The weird controls over here, intensity, focus, and illumination. Well, the intensity and focus are talking about that electron beam. It's how many electrons are in the electron beam. And you need to adjust that sometimes because if you're sweeping very fast, the beam isn't there for very long, and so it doesn't produce a very bright spot, and it might be very hard to see. So you have to turn the intensity up if you're sweeping faster. The focus is a control of how much the beam spreads. Again, there's some electrical focusing, and you have to twiddle that knob to get things to work. One important thing is that the oscilloscope inputs are coming from these standard oscilloscope probes, which have a ground lead, which I'm supposed to connect to ground, and a connection here, a little hook, or that hook can be removed and then you get a little point for connecting up to the signal you're interested in. You should always hook up this ground lead to ground so that you don't have sort of a floating long wire to ground. There is a switch on the standard probes also that says ×1 or ×10. And what that does is it controls the impedance of the probe. The standard probe is usually a 1 mega ohm impedance, and for a lot of stuff you're doing, that's great. But sometimes you're looking at something that is a high impedance source, and you want to go to the 10 mega ohm impedance instead of the 1 mega ohm impedance. There's also capacitance in parallel with that 1 mega ohm, and by going to the ×10, you divide that capacitance by a factor of 10. And that's very important if you're looking at high frequencies. For the very low frequencies we're looking at, we don't really need the ×10 probes. The disadvantage of the ×10 probe is that the whole thing is done as a voltage divider, and so the ×10 probe is giving you a 10-fold reduction in the voltage that you're looking at, and so you have to compensate for that by using more amplification in the oscilloscope. And once you start looking at very small signals, you might end up getting to the point where you cannot see your signal because your oscilloscope doesn't amplify enough. So we're not going to be using these probes in this class because we don't need the high speed that you can get from the ×10 probe, and if we're just doing ×1 at low speeds, plain wires work just as well as these more expensive oscilloscope probes. Okay, I think I've shown you about all you really need to have some appreciation of what an analog oscilloscope is about, and so I'll stop here and we'll do another video on digital oscilloscopes.